This video will run through the concept of shortest paths in the context of network and decision mathematics in Module 2 of VCE Further Maths. It will also include some examples of the Dijkstra's algorithm. Firstly, what do we mean by shortest paths? So often when we're analysing networks or graphs, particularly weighted ones, we're looking to find the most efficient path between 2 points or 2 vertices. And there's 2 main methods that we use. The first one is by inspection, and that just means simply we are looking at the graph, inspecting the paths and making a decision about which path we think is the shortest. The second method is Dijkstra's algorithm, which is a set of rules or steps that help you work your way through systematically to find that shortest path. Let's look at this by inspection method. It is pretty much a trial and error method, but it can be the easiest way to do the shortest path for the most simple networks. So a simple graph that we've got like this, where there aren't too many paths. If we're looking to find the shortest path from home to university, what we can do is actually check every possible pathway through and find the weight of that. So the total distance would be those weights added together. So 2 plus 4 plus 2 would give us a total of 8. And then seeing if we can find a shorter or quicker way to get from home to university. So we can see there we've got a path of 7. So it is a little bit of trial and error, but as I said, it can be a quick and easy way to find the shortest path from point to point when you have a very basic sort of network. So not big numbers, they're easy to add quickly in your head and calculate, and there's not too many different possible pathways through. Alternatively, we have Dijkstra's algorithm. It's a more systematic approach. It can, however, be time consuming. So it is important to practice and know how to use it, but then also to make your best decision about how to use your time. So if it is something that you can see that's a bit more complex, the network, or the numbers are not nice, easy ones that you can simply add in your head as you go, the Dijkstra's algorithm might be the best possible answer or the way to go. The advantage is once you finish the algorithm, you actually get both the path and the distance in the final answer. And then you always want to go back and check on the graph itself. So we'll have a look now at the example here using Dijkstra. The method I use for Dijkstra's algorithm is the table method. So what I need first is a table setup that I'm going to fill out, and I'm going to work my way across each row considering a starting point. So in this case, I'm being asked to find the shortest path from home to university. So my first starting point is at home. I then write the remaining vertices across the top of the column headings here. So I put in vertex A, B, C, D, E, and the university. And so what I'm going to do in this first row for home is check any of this one-step direct connections. So we're only talking about adjacent vertices here, that direct connection. So from home, I can see that there is a direct connection to vertex A, and it has a weight of 2. So in the box here with home and A, I'm going to record that distance. I can then also see that there is a direct connection from home to vertex C, and that has a weight of 3. So again, home and vertex C, I record that weight of 3. In this graph, there also is no direct connection from home to any of the other vertices. So there's no connection to B, to D, E, or the university. So I represent that with a cross in my graph, or just a dash if you'd like. It's best not to leave it blank, because if you leave it blank, you might think you've left something out, so you've made a mistake, whereas you haven't. So my next step is to look at these distances and isolate or identify the smallest distance, because remember, I'm wanting always to find the shortest path. So that shortest path, that smallest distance, becomes my new focus point. So that means that vertex A becomes the next point at which I'm starting my journey. So I copy that value down. I tend to put a box around it to highlight that that's the value I'm now working with. And A becomes the next row heading. So now I've traveled a distance of 2. I'm now at vertex A, and I'm going to consider all of the direct connections to A. So from A, I can travel to B directly with a weight of 4. Now I have to remember I've already traveled a distance of 2 to get to A. So I have to remember the value that's in the box is what I've already traveled, plus an additional 4 units to get to B. So that means the total distance from home to vertex B through A is 6 units. I then consider the other connections from A. So A also has a connection to C. That connection is 2 plus the 2 units already travelled. So that would be 4. But I want you to stop and think. I already identified in the previous row that there was a better way to get to C from home. So what we've actually identified here is that I can go from home via A to C, and that would take 4 units. Or I could go home directly to C, and that would take 3 units. Now I want the shortest path. So 4 is not the shortest. I'm going to take the number from above and bring it down, because that was already a shorter path that I identified to get to C. I now continue on A to D. So again, I've already travelled 2 units plus 2 more to get from A to D. So that's a total of 4. I cannot travel directly A to E or A to the university. So again, I still have no pathway there. So once I've completed my row A, I now again am looking for the next shortest path. And so I can see that this pathway to vertex C, that value of 3, is the next smallest number. So my next focal point becomes vertex C. And I start my process again. So from vertex C, I've already travelled the 3 units, the shortest way to get there. I don't have a direct connection to B, so we bring down that pre-existing path that I know I can get to B in 6 units. D, C to D, again, no direct path, but there's already a pre-existing pathway to get there in 4 units. C to E, there is a direct connection, and so that is 1 plus the 3 already travelled, so 4 total units. And finally, there is no direct connection from C to the university and no pre-existing path, so again, we mark that with an X. Again, I now look for the shortest path, or the smallest value. And you can see I've got 2 options there, either vertex D or vertex E. It actually doesn't matter which one you choose. You can choose either one because you will end up using the other as part of the process. So I'm just going to take D because it's the one on the left-hand side for no other reason than that. D becomes my new focal point. Now you might be wondering why I've crossed out underneath in green these columns for A, C and D. Effectively, once I've identified them as a shortest way to get to that vertex, I no longer need to keep revisiting it. I only revisit if the vertex hasn't become the focal point. So I tend to just cross it out so that I can visually see I no longer need to check that. So I'm not doing more work than I need to. Okay, so we're now at vertex D. The quickest way to get there was through A, which was 4 units. And so now I'm considering direct connections from that point. So D to B has a direct connection, and that is 2, so that's a total of 6. That's equal to the previous established pathway through A. So we put the number 6, and it's actually, there are 2 ways to get there in that amount of time or units. D to E. So from D to E, there's no direct connection. So I take the established pathway from above, so 4. And finally, D to the university. First time we have a connection there. So altogether, we can see that that pathway, the 4 pre-existing plus 3 to the university, is a total of 7. I repeat my process. So you can see I'm repeating the same thing each time. Identify the smallest value, which is 4. And that came from vertex E, so E is my new focal point. I'm now at vertex E in that pathway of 4. I have no direct connection to B, so its pre-existing path stays put. And my connection to the university would be a pathway of 8, but we previously identified a shorter way to get there in 7 units. So we ignore the 8, and you can write that down if you want so that you can refer to it, but we have a better way of getting there. So now again, identify my shortest value or my smallest value. B becomes my new focal point, and I'm going to finish my final row. So we've said we can get to B in 6 units. There's a direct connection to the university in 2 units, so that would give us a total of 8. But again, we already have a previously established shorter path of 7, so that will be the value I stay. It's the last number left, but 7 is the smallest number there, and it came from the university. So you don't have to do this final step where you write your end point as your row header, but it can be useful for our final step. So how we put all of this together is I can now identify from my table that the shortest path is equal to 7. Okay, that was the value that I ended up with at my finish point of the university. So my shortest path, the value of the shortest path, or the weight of the shortest path, is 7. Now if I wanted to identify the path from the table, I did say that the table also, or your answer also, gives you the path itself. So I have travelled from the university. I'm going to work my way backwards. And so I've got a number 7 here. I'm going to come up the column for university to where that 7 originated from. And then I look at the row heading and I can see it originated from vertex D. So I come across my row so that now I'm in column D. So I'm in that space where D crosses over. So now I'm looking at the number 4, and I'm going to travel up column D to find where the 4 originated from. And the 4 originated from vertex A. So again, I'm going to come across this row until I'm in column A. Now I'm looking at the number 2. I travel up column A to where the 2 originated from, and look where that 2 was allocated from, and that was from home. So if I read now from the top down, I can see home was the first vertex, my start point. The next horizontal line is vertex A. The next horizontal line is vertex D. And then the final horizontal line is the university. So that tells me my path was home, A, D, to the university. So home, A, D, university. And I can see that if I add the weights on that edge, on those edges, that gives me a total distance of 7 units. So I've identified the shortest path. I've found the weight of that shortest path, and I've been able to match that from the table to the values on the graph as well. So as I said, Dijkstra's algorithm, it's very systematic. It's quite repetitive. So once you understand how to use it, you can do it very quickly. But it may be that you actually found it easier to do or to find that shortest path by eye. So it becomes a choice. What is easier for you? What's quicker for you? I'm going to run through another example here. So this one looks a lot more complicated because it's bigger. It has more vertices. So again, you can do by inspection, but the purpose of this is just to show you another version or another example of Dijkstra's algorithm. So here we're finding the shortest path, again, from the entrance to the cafe. So we've got our cafe in here and our entrance on the left-hand side. So before we start, we make our entrance our first focal point, and then we write the column headings are the remaining vertices. And from memory, this example comes from an exam where we were looking at a zoo. So each of these letters, the vertices represents a different animal enclosure in the zoo, and our cafe to end. So I tend to put the finish point where we want to end up as the very last column, just so that you sort of work your way through orderly, but it actually doesn't matter as long as you just have all of the others listed across the top. Okay, so working our way through from the entrance as our focal point. So again, entrance, direct connection to P is 25. So we can write 25 in the box there. Working across, there is no direct connection to S. There is no direct connection from entrance to Z. There is no direct connection to B, E, M, T. Now there is to G. We've got a direct connection of 45. And there is to L, a connection of 35. No connection to the cafe. So of our options there, let's take the smallest value, so 25, to P, which I think was penguins, and that becomes our new focal point. So if I've travelled the 25 to P, and I'm now looking at direct connections from that point on. So P to S is another 20, so that's 45 in total to get to S. P to Z is 30, so that's 55 in total, 25 plus 30. There's no connection to B, to E, to M, to T, to G, so we take the already established 45. No connection to L, so again, the already established 35, and no connection to the cafe. I look at my row P and find the smallest value, so I have 35. So now L becomes my new focal point. So L becomes my row heading, and now I'm going to work through connections to L. So again, I've gone from the entrance to L in 35 and looking at the paths to the next connectors. So there's no connection from L to S, but we already know there is a path of 45. No connection from L to Z, but there is a path of 55. No connection to B, E, M. There is a connection to T. That's 35, so that's a total distance of 70. And there is a connection, L to G, of 15. So that would be 50. However, we've already established there was a quicker, shorter path with that direct connection. So the 45 is what we note down. And again, no connection to the cafe. So now we look and we can see there's two 45s here. Now, for the sake of doing it differently, I'm going to take the connection at G, just to show you that it won't matter whether I choose the left-hand number, the right-hand number. So G will become my new focal point. So I've travelled 45 to G. I have no direct connection to S, but a pre-existing established path of 45. No additional direct connection to Z, but I have that existing path of 55. No connection to B or E or M. I have a connection of 55 to T, so that would be a total of 100. However, we have a shorter way of getting there, a quicker way, going via L. So we note down what we already had, which was 70. And finally, no connection from G to the cafe. So at this point, we can see our next smallest number is this 45 for S. So it didn't matter that I chose G. The next vertex I'm concentrating on will be S. Had I chosen S, the next vertex I'd be concentrating on was G. So you will end up doing them back to back. Okay, so now my focal point is S. I've travelled 45 to get there, and now I'm looking at the next connections. So S to Z, there is a connection, so that will be an additional 25, so 70, but we've already established a shorter path of 55. S to B, 40, so now we have that total pathway of 85 to get to B. S to E, no connection. To M, no connection. To T, no connection, so the established path of 70. And to the cafe, no connection. So again, our smallest value is 55. So I'm now at vertex Z as my focal point. So I've travelled 55 to get to Z. Direct connections to B, there isn't one. So we've got our established pathway of 85. Z to E, no connection. To M, no connection. To T, no connection. So our established path of 70. And to the cafe, we finally have a connection to the cafe. So that's an additional 40. So 55 plus 40 gives us 95. Okay, so now we have a connection to the cafe, but we can't jump straight to the end. We have to keep following our process through. And so our next smallest path is 70 to T. So T becomes our focal point. We've already travelled 70 to get to T, down through L. And now looking at connections from T. So T to B, there's no direct, so we take the 85 already established. T to E, no connection. T to M, yes, we have a connection there of 40. So that's 70 plus 40, 110. And T to the cafe, no connection, so we take our established 95. Again, our next smallest number, 85. And so now B becomes our focal point. So we've travelled our 85 to get to B. Looking to see, is there a connection to E? Yes. Okay, so that's 60, an additional 60, so 145 total distance. To M, there's no connection, so we take the established 110 from above. And finally, B to the cafe, 25. And so we can say 85 and 25 is going to be 110. That's bigger than the previously established 95. So we go with 95. Our next smallest number, finally 95. So we've hit the cafe as our focal point. As soon as we get our finish point as our focal, we can stop. Our process is done. And so now we can say, well, we know that the shortest path will be, or the length of the shortest path will be 95. What that path is, if we go from the table, so we're at the cafe and we're looking at where going up until the 95 was established. So where did it first appear? It first appeared at vertex Z. So I go across to column Z. Now focusing on the 55, and I'm going up the table, up the column until I get the first 55. And that came from P. So I go across to column P. Now looking at 25, I go up to where that first appeared, and that came from the entrance. So reading now from the top down, where are the horizontal lines? They're at the entrance, then P, then Z, then the cafe. So that should be my pathway. So the entrance to P to Z to the cafe. And I highlight that, P, Z, cafe, and make sure that those values add up to the value I have, 95, and they do. 40 plus 30 plus 25 gives us 95, and that's our shortest path from entrance to cafe. So again, that's quite a big, long one, which may have been quicker to do by eye, by just checking some possible pathways. But the difference is between a little bit of trial and error and feeling you're happy with an answer versus a very systematic approach that might take longer, but will, if done correctly, guarantee you the correct answer. So there's some options there. I encourage you to have a look at some other videos going through some additional examples of Dijkstra's algorithm, and it's just about practice to feel comfortable and confident with it. Okay, that's it for this video. Thank you.